going to turn it over to Assistant Professor Carey Melkovich, and he will be presenting on how Google works. We'll do about a 10-15 minute talk and also give us a little bit of an overview of the departmental workings of the Mathematical Sciences Department. And so I'm going to let you take it away, Carey.
All right. Thanks so much, Carey. So, hey, I'm Carey. Thanks for coming. So as Carey said, I'm an assistant professor in the math department. So we have many research interests represented in the math department. With the Q&A, we'll be talking a little bit about the programs and the offerings. I guess I should briefly mention, we of course have a major in mathematics, both a BA and a BS. We also have both a BA and a BS in actuarial science and a new BA in statistics. So we'll be talking more about that later and answering some questions. Before I get into the presentation, let me just tell you a little bit about our department research-wise and a little bit about myself. So we have a lot of research interests in the department. Mine is in the subject called topology. It's the study of shapes, but it's kind of the study of squishy shapes. So if you're familiar with geometry, right? I'm sure you've seen geometry before at some point. In geometry, you're studying shapes, but you're looking at their lengths and their angles, that kind of thing. In topology, we throw that all out. We say in topology, a circle and a square are the same shape. And that might seem really crazy and ridiculous, but it actually turns out to be a good idea in a lot of settings, especially if you start to think about high dimensional shapes and how do they work. By focusing just on a shape, how a shape is connected together, sometimes this makes things a lot more approachable. Right? A circle and a square are the same, of course, because they're both a path that links up to itself. So of course, if you have questions about that, that's not really the subject of the presentation today. But of course, you can also ask me about that. So here at Binghamton, I also do teaching, both for graduate and undergraduate classes. One of my favorite classes to teach is linear algebra. And so I decided to pick that as the topic for the presentation today and tell you a little bit about how linear algebra is everywhere, including when you Google, when you search the internet, linear algebra is happening and you don't even know it. So let me tell you about that. So let me switch over to how Google works. Okay, so let me begin this presentation with a question. Let's start with a question. Before I tell you how Google works, I would like for you to guess. Thank you, Carey. Yep. So here are 4 options. Does Google just search through pages and look for how many times your keyword appears? Or does it count the number of visitors who are currently at this page? Does it count how many links are pointing to the page? Or does it work by employing an army of monkeys who are ceaselessly clicking around through the internet to find your page? So go ahead and take a guess. Okay, so we got a pretty good spread of responses here, which is good because this was actually kind of a tricky question. So to some extent, actually, all of these things are used, but they're kind of used to different degrees. So to some extent, Google does use the presence of keywords. To some extent, Google does use how many links are pointing to a page. So in a sense, they're all kind of right and they're all kind of wrong. This is a bit of a trick question, but maybe C is the closest. If you wanted to give an approximation to what they're doing, a good approximation is, well, they're counting how many links point to a page. But that's not exactly right. I'm going to try to explain a little bit closer to what's right. It turns out, though, I want to congratulate whoever voted for D, because to explain what's right, it turns out that D actually ends up being a little bit closer. It's a really good way to imagine how their algorithm works, is to imagine that they actually have 1,000 monkeys or 1,000,000 monkeys working for them, clicking around through pages on the internet. So let me explain that. So for simplicity, when we do mathematics, we always like to make simplifying assumptions so that we can understand a core idea. So let's simplify and let's pretend that there are just 4 pages. Out of all the pages on the internet with text matching my keywords, I don't know, I'm searching for cat video. Okay, so type in cat video. So along all the pages that might be relevant, there are just 4 of them. And they're drawn in this diagram. And I want to look at this and try to figure out which of these is the most relevant. Which one should I be putting at the top of my Google search? Now, I'm sure a lot of people visiting here are fairly young, and for you, Google has been around for forever, but I remember what things were like before Google. Before Google, search engines were terrible. They're awful. They were so bad at finding a page that was actually relevant to you. And Google had this way of just just magically finding the thing that you actually needed to find. So, okay, so we have these 4 pages. How are we going to find the most relevant one? Okay, so here's the idea. I have an army of monkeys, 1,000 monkeys. I'm going to set a computer in front of each monkey, and I'm going to set it to work. That computer is pointed at one of these web pages. And every second, that monkey is going to click on a link at random. So say the monkey's at B, it's going to click on the link, follow that arrow, go to D. Next second, it's going to click on the link, go to C. Next second, it's going to click on the link, go to A. The next second, it's going to click on a link at random, so it'll go to B or D or C. So it'll keep going like this. And 1,000 monkeys, they're all on different pages, they all keep clicking away. I'm a mad scientist, I can do this. Okay, so let's keep track of what the monkeys do. So at time 0, that's the first column of this chart here. It's time 0, I have 1,000 monkeys and they are evenly distributed. So I have 250 monkeys on each web page. And then column 1 is what happens after they click once. So now I have a lot more monkeys on page A, a lot less on page B. Then time 2, they click again. So you notice the number on page A doesn't change, but the monkeys are moving around. Like some of the monkeys on page A are leaving, and then other monkeys from other pages are coming onto page A. So this is a dynamical system. The monkeys, they're very active. They're moving around for a long time. So I set them off, I let them do this, and I just let them run for a while. You know, I'm a mad scientist. I have an army of monkeys. I recline in my chair. I let them run, sip my lemonade. And then after a while, I come back. So after a long time, I come back. And now I look at each web page and I count how many of my monkeys are on that web page. So here I am after 100 turns. This last column here, that's the number of monkeys I have on each of these pages. Okay, so maybe this next one's a bit of a softball question, but if you had this army of monkeys and this was the result you saw, how would you rank them, right? Which web page would be the most relevant? This one is not a trick question. All right, so lots of people voted A, and A, of course, is the correct answer here. Why is A the most relevant? After a long period of time, A has the highest number of monkeys at that page. So in fact, I don't just know that, but I actually have a whole listing. I can say A is the most relevant, and then C, because that is the next highest, and then D, and then B. So I can get an entire ranking. So what's going on here? So earlier, you know, some of you said, oh, I think maybe it has to do with counting the number of links. And that's sort of what's happening, but it's not exactly it. So the idea is that to figure out which web pages are important, it's more important when it has more links pointing to it. Because the more links you have, the more your monkeys are going to get directed to that page as they're randomly browsing around. But that's not the whole story, because a link from another page that is itself very important. So a link from an important page is going to have more weight than a link from an unimportant page, right? So after a long amount of time, the pages will have different numbers of visitors at them. A link from a page with lots of visitors is going to count more than a link from a page with not very many visitors. So that's the essence of the algorithm. It's sort of counting links, but it's counting links with weights. And the easiest way to visualize it is to have a bunch of random surfers randomly browsing the internet. After a long time, the most relevant result is the one that has the highest number of visitors. That's how Google works. Surprisingly simple, right? Now, there's one drawback to this idea, and that is that I don't actually have an army of monkeys. So how do I make this idea work? I use linear algebra instead. So linear algebra is one of the core subjects that you take in your college mathematics curriculum. It's just the study of linear functions in several variables. And what does it have to do with our monkeys? So in this case, I have one variable for every web page. So if there are 4 pages on the internet, I have 4 variables. And those 4 variables are changing in time. This is a bit more complicated than what you usually see in high school, where you have just 1 or 2 variables that are changing in time. If you have 10 web pages, you have 10 variables. If you have 6 billion web pages, you have 6 billion variables. So you have lots and lots of variables. So linear algebra is a language for talking about and organizing these things. So one thing we do is we organize that list of variables into a single object that's called a vector. Okay, so that vector lists how many monkeys you have on each web page. And then the vector changes over time. Right? So we are having a function that's taking that vector to a new vector and then taking it to a new vector, and it keeps going over and over. Each time it changes by a matrix. So if you've seen this before, it's a rule that takes each vector to a new vector. And how do I compute each entry of that new vector? It's a linear equation in the original vector. So this is the essence of what linear algebra is. You're studying linear relationships between variables. What makes it complicated is that there could be many variables. Okay, so every time I multiply by this matrix, I go for a very long time and I'm looking for a limiting behavior. So I'm looking for some arrangement of my monkeys on my web pages such that when I apply the rule one more time, nothing changes. Like the monkeys all shuffle around, but the number of monkeys on each web page doesn't change. And in linear algebra, we call that an eigenvector. That's a vector that when I multiply by the matrix, I actually get the same vector again, maybe multiplied by a fixed number. And now it turns out I can just solve for V using linear algebra. So I don't actually have to run the simulation to figure out what V is. So that's where linear algebra shows up. If you happen to have an army of monkeys, great, good for you. If you don't, you can use linear algebra. So this is actually not the only application. Linear algebra has tons and tons of applications across mathematics and the sciences. It appears anytime there are many variables. So in fact, another way of thinking about this that's kind of cool and trippy is that several variables is the same thing as higher dimensions. So to make that analogy, if I have a vector, remember that's a list of numbers. If I have a vector with 3 coordinates, that's the same thing as a point in 3-dimensional space. Right? That's your X and Y and Z. Okay, if I'm going to search 10 web pages though, I'm counting the number of monkeys on each web page. That's 10 numbers. So geometrically, that's a point in 10-dimensional space. You might not realize it, but when you're doing a math problem that has 10 variables, you're actually working in 10-dimensional space. And sometimes geometric intuition can be helpful here. Of course, the actual internet has 6 billion web pages. So this is an incredibly high dimensional problem. You're working in a 6 billion dimensional space. So higher dimensions are actually everywhere. You might be, when someone says higher dimensions, the first thing that people usually think of is, string theory, extra dimensions, that kind of thing. That's true, but that's not the only place where this shows up. Higher dimensions show up everywhere, across mathematics, across science, across statistics. Higher dimensions are everywhere. Just to give a quick, very relevant example, suppose you want to study a disease, such as, I'll pick a disease at random, coronavirus. You have a group of patients, for instance, who have had some medical outcome. For instance, maybe they haven't fared well with the disease, and you want to study, well, what do they have in common, right? Like what factors affect how people react to this virus? Well, for each patient, you're going to want to collect as much data as possible. So you collect data about where are they located, how old are they, all kinds of vital signs. This data becomes a long list of numbers for every patient. If you think about it, though, that means that every patient is a point in 10-dimensional space. And when you're trying to understand what pattern they form, you're actually trying to do a geometric problem in 10-dimensional space. Right? For instance, you might say, what shape do they form? Is there some kind of line, a plane that they all line along, something higher dimensional? This is a technique in statistics called principal component analysis. And again, it's based on linear algebra. So it's, again, this idea that this kind of mathematics is everywhere. This is a much more sophisticated analysis than studying each variable separately. You can look for patterns that correlate between the variables. So like maybe it's not just age, but maybe age corresponds to something about your immune system, and these other variables also correspond to that too. So you can tease out more sophisticated patterns by doing this kind of thing. So the takeaway that I hope you bring from this is that 1, having an army of monkeys is cool. And 2, that we actually live in a high dimensional world. What you do even something like trying to figure out the most relevant search result for your internet search, you're solving a problem that's taking place in some high dimensional space. High dimensional math problems are everywhere. And linear algebra is this language that we use to talk about high dimensions. By taking that problem and organizing it to the language of vectors and matrices, we can effectively solve it using methods that are very similar to the methods that you learn to do one variable equations in high school. So this is a toolbox. It's one of the core courses in the math major, and for good reason, because we use it all across mathematics and all across the sciences. So yeah, so that's my spiel about Google and linear algebra.
Thank you so much, Carrie. I think we're going to maybe get started with some questions here. And if anyone else has questions, they can feel free to join in on this question and answer problem. But we're going to maybe start with one of the questions related to the topic here. Is linear algebra a component of graph theory is the question.
Absolutely. Yep, there are. So graph theory is a huge subject. It's, oh, you're welcome. Graph theory is a huge subject. It's impossible to give a complete description of all the techniques that are used. But yes, linear algebra is used substantially in doing graph theory. For instance, associated to every graph, you can form a matrix called the incidence matrix. And it turns out that from this matrix, you can compute two numbers, one of which is the number of components in the graph. So it's telling you like how are 2 points connected together or not in that graph. And the other is essentially a count of the number of cycles, a count of the number of holes in the graph. So linear algebra gives you an algebraic way of computing those. It's an algorithm, so you can actually just feed it into a computer and you can have a computer figure these things out for you.
Thank you. Another question we have here that's I think a little bit more math topic related. Can you specify what weight is and how it's a factor toward relevance?
Weight is a factor towards relevance. Oh, yeah. So weight, the term weight I was using a little bit informally. So if you look, so this presentation is based on the original paper that Larry Page and Sergey Brin and their advisor posted around the time that they had created Google and Google was starting to become really famous. So in that paper, they just used the term relevance. But the subject of that paper is relevance is kind of this nebulous concept and they're trying to pin it down mathematically. So they're trying to say, okay, what is relevance? I don't know, but here's a method for something we can compute that seems to line up with relevance. And in the presentation I gave, that number turns out to be the number of monkeys on your webpage. Right, so that number is Google's best guess for the relevance of your webpage. It's what their algorithm spits out.
Great. So we have a question here about when to take maybe linear algebra before or after multivariable calculus. So maybe we can broaden that question to what the curriculum structure looks like in the math department. You know, what's a typical math major structure? What are the first level, you know, freshman, sophomore classes? What are some of those higher level classes? And what
yes, excellent. So in the math major, you have to take, so the core classes include calculus 1 through 3, linear algebra, and number systems, which is an intro to proofs class. So there's generally flexibility as to when you can take these. Like I know, for instance, a lot of students take linear algebra 4 proofs, a lot of students take proofs before linear algebra. For multivariable calculus, it depends on the class you specifically take. I generally like the idea of people taking linear algebra before multivariable calculus because, like I said, it gives you a better language for how to talk about higher dimensions. Like once you know linear algebra, you know how to talk about linear transformations, like how to go from one vector to another by a sequence of linear equations. Once you know that, you can revisit the idea of the derivative and you realize that the derivative of a function is just taking a function which is not linear and approximating it by something that is linear. So the derivative is most naturally a linear transformation. And for a multivariable function, the derivative is really a matrix. So I believe so it depends, I would have to look in the details. And this is, for specifics of exactly when to take each class, it's good to also check with you. I'll be posting some links that have a lot of details in the classes that you can peruse. So it's good to, you can check with me, you can check with the director of undergrad studies, just in case I say something during the live presentation that, but what do I want to say? Yeah, so I generally think it's a good idea, but I think it's set up so that you can take multivariable calc first. Because a lot of times your first multivariable calc class, you just talk about partial derivatives. So you do it in a way that you don't necessarily have to have linear algebra first. It's just kind of more enlightening if you've seen linear algebra.
Okay.
Sorry, it's a bit of a long answer.
That's okay. That's okay. I think it's good to learn more about the topic, and that's why our students are here. So maybe let's move into some of the application side of things. We have a question what some applications of linear algebra are in physics, but maybe we can expand that question to what are
there are tons
of the math. Yeah. What are some of the applications of the math major? Once students leave Binghamton, what are some trajectories that some of your past students have gone? What does this degree kind of give you, coming from Binghamton?
Yeah, so the math major is a nice major because it really opens a lot of doors and it closes very few. From the math major, you can go on into academia, you can go on into teaching. Those are kind of obvious things to go on into, but you can also go into tech, you can go into finance, you can go into insurance, you can even go into law. The math major is good preparation for a lot of different career tracks because mathematics, you learn some content, but a lot of what you're learning is also how to think very precisely, like how to take a problem and break it down to constituent parts and simplify and like focus on the core issue and then say, okay, how do I solve this? And that's a really useful skill across a lot of different industries.
Great. And maybe can you give a couple of examples? I know we had that question about the applications of linear algebra in physics specific.
Yeah, so there are a lot, but one of my favorites is in quantum mechanics. So actually, it's actually kind of hard to say what it is because, how do I say this? Quantum mechanics is secretly entirely linear algebra. Like the entire subject is just linear algebra in disguise. It's kind of amazing. But to be a little bit more specific, so there's this equation in quantum mechanics called the Schrödinger equation that you have to solve in order to tell how a particle or some other really small object is going to evolve over time. This equation is an example of what's called a partial differential equation. So you might have seen an ordinary differential equation. I have a function and I have some equation relating its derivatives. I try to figure out what the function is. The Schrödinger equation is different because it's an equation that is relating derivatives in many different variables at the same time. And we're really bad at solving these things. They're so hard to solve. The main technique, though, for solving the Schrödinger equation is actually from linear algebra. You rewrite the equation as something linear. It's called a linear differential operator applied to your wave function. And then you do what's called diagonalizing the operator. So you actually look for these eigenvectors, the operator. You look for particular wave functions that are nice, simple solutions. And then you take the wave function you actually started with, you decompose it in terms of those, apply the operator, and then add the results back together. So linear algebra is it's actually essential to do in quantum mechanics. We wouldn't even be able to do it without it. And it's not just in quantum mechanics. In every branch of physics, there are substantial applications of this thing. Like I said, it would take me like an hour to probably go over all of them. So I'll just leave it at that for now.
The brief explanation. Yeah. Is appreciated.
Yep.
So you mentioned there are a lot of applications. So one of the questions here is, are those analysis techniques that you talked about, can they also be used in life sciences for, biology experiments, that kind of thing? Maybe you could talk about a little bit about how, the math major or, a math minor might pair with some of the other offerings that Binghamton has, and what are some of the common pairings that you see there?
So, yeah, so one part of, how do I say this? So depending on what you focus on in mathematics, so we have, for instance, a statistics major in the mathematics department, and that is focused on, what is statistics? It's analyzing data sets, right? It's looking in data sets and looking for patterns. So that gets used anytime you have a data set. Now, I'm not a biologist, but I think that when people do biology, there are data sets. I'm gonna wager money on that. And so therefore, techniques from mathematics and techniques from statistics are useful there. Especially, like I said, a lot of times, anytime you want to be more sophisticated than looking at one variable at a time, you're thinking in terms of several variables. And this is a place where it's really helpful to have knowledge from a subject like linear algebra. This is why I wanted to present specifically about linear algebra, because it's one of these crossover subjects. It's one of these subjects where if you understand it, it really helps in a lot of different subjects, including biology and the life sciences, because it gives you a more sophisticated understanding of how data works. So you can probe and see more sophisticated patterns than if you're being kind of clunky and simple and just looking at one variable at a time.
Great. Could you also, we have a question here about explaining what number systems exactly is and how that factor in.
Yes, number systems is an introduction to proofs class. So calculus 1 through 3 are not based on proofs. They're more like what you think of when you think of a calculus class. Like you're going over the content, you're doing exercises, like take the derivative of this, take the integral of this, and so on. So number systems is a gateway class for the higher level math classes. In the higher level math classes, this is actually a bit of a surprise. At higher levels, mathematics starts to be a little bit more like the humanities than you would think. It's a little bit more about reason and argument, and not just seeing a pattern, not just getting the right answer, but being able to argue for that right answer. Being able to say, you know, this is why I know it's correct. So number systems is a class that prepares you for that. It's a class on how to read proofs and how to write proofs. And you might have seen proofs in geometry class, like 2-column proofs. It's not exactly that. The essence of writing proofs is just taking an idea that you've seen. Like you've seen a pattern, you recognize and understand it, being able to write that down and communicate it to someone else in very precise terms. Being able to say, like, this is true, I'm sure that it's true, and this is why. So that class is an intro to proofs class. It gets you used to that idea of writing proofs. And then all of the higher level math classes after that use that technique, right? When you present solutions in higher level math class, you present them as proofs. So it's not just I found the answer, but I can explain to another person why the answer is right. So that's what number systems is.
Great, thank you.
Yep.
And another exploration into other mathematics classes and maybe their topics. We have a question about what the best mathematics classes would be for someone interested in AI technology or robotics and maybe some of those fundamentals.
Ooh, I don't know. I'd have to think about that.
Okay, maybe that's
I can say for sure that,
yeah,
I can say for sure that, like, for almost any question, like, do you need for science blah, like linear algebra, definitely. Linear algebra is one of those things, like, absolutely, it's a good idea to take. Beyond that, it depends. So actually, I have heard that topology actually shows up in robotics in the area of motion planning, because when you plan the motion of a robot arm, you have to take the space of all possible configurations and break it up into coordinate charts. So topology, which is an example of a higher level math class, is actually helpful specifically for that. But yeah, I would have to think about that more to comb through the course catalog and to say, oh, take exactly this and that.
No problem. I'm going to jump back to another topic-related question, kind of about Google. So the question is a probabilistic approach applicable to refining search results in Google based on user data and showing specific ads to certain users? So maybe you can.
That is a good question. So Google obviously has done a lot of stuff in addition to the thing that I presented here. So the thing I presented here was just the very first paper that they wrote. It was the first idea that was the foundation for the search engine. I think this was before they even had ads. Since then, obviously Google is a big company now. And so since then, they've refined on this idea a lot. And a lot of the refinements are proprietary. So I can't tell you with complete certainty what they've baked into their algorithm now. I'm not sure if what Google uses to determine the relevance of ads. I do know that so this is highly related, that when you look at Netflix is doing something similar, right? They are looking at all of your past usage, things that you've watched in the past, and then they're trying to predict what you'll watch next. So I'm going to presume that when Google is recommending ads, maybe they're doing something similar. So I do know that Netflix, again, this is a very complicated problem. The solutions that work are generally engineered together from a lot of different ideas. But almost always at the bottom, the basic idea that you start with is a linear algebra idea. So this thing that I mentioned, principal component analysis, is one of the basic foundational ideas that figures into that Netflix problem. So again, like your users are fitting some kind of line or plane of best fit. And when you know what that line is, then if you know some of the ratings, right, knowing that your user stays close to the shape, you can then reverse engineer and say, oh, therefore the ratings for all these other movies must have been these. So this allows you to predict how they will react to future things that you haven't exposed them to yet, given incomplete data about their past experiences.
So actually moving back to the past, I guess there's a separate here. If Google uses linear algebra to find relevant web pages now, what did search engines use in the past? Why were they not as efficient?
Oh, very good question. So let me see, do I know this? I think, so I'm not 100% on this, but I think what engines like Yahoo or AltaVista were using before Google was they were sending out crawlers, they were indexing the web, they were downloading copies of web pages and the content. And then when you searched for a search term, they just searched through their database and they just looked for which pages had that term in it. Just totally disconnected from each other. How many instances of this search term are on this web page? And you can see how that could be problematic, right? You could have a really low quality page that just has the word a lot and that isn't linked by a lot of other pages. Whereas when you do Google's thing and you actually track based on, how likely a user is to end up at that page, it's just kind of magic. You just end up getting the page that is actually more relevant to you. So I think, I'm not 100% sure. I think that's how they worked before. What I do know, because I was alive during this page, and I did use the internet before Google was around, is that the other search engines were terrible. They were so bad at finding like anything relevant to what you actually want to find. When Google came around, it was amazing. Like no one could believe that it was possible to make a search engine that actually worked. I mean, now of course we take it for granted, like all technological advances. But at the time it happened, it was amazing. It was completely amazing. And of course, it completely changed the internet. The internet as we know it today wouldn't have happened if a good search engine like this hadn't come along.
Mm-hmm. So I'm going to jump back to a little bit more about Binghamton now and
Sure.
some of the other opportunities in the undergraduate. So I'm going to kind of join two questions in one. What does research in math look like, and can undergraduate students take part in it? And then you could talk about the path to working in academia and maybe some of the other higher level, whether master's or PhD programs that Binghamton offers as well, and paths towards
Yeah. So what does research in math look like is a good question. I feel like in general, the public doesn't really have a clear idea of what it is that mathematicians do. And I think it has something to do with the way that we teach math in school. Like we present mathematics as the sequence of things that you're just supposed to memorize and learn. But that's not really what mathematics is. Mathematics is about exploring the world and finding patterns and being able to prove that you have those patterns, like being able to locate the pieces that make the pattern work and see that it works, and then being able to exploit those patterns to do magic, crazy stuff that you couldn't do before. And so research in mathematics is about finding interesting problems that have to do with finding new patterns that no one has seen before, and then actually finding those patterns and actually saying, yep, this really actually happens. So just to give an example, like I work in topology, so I study abstract shapes, and I am always looking for patterns that exist in these high dimensional shapes. And every time I find a new pattern, I get really excited and I want to go around and tell everyone about it. It's like go around and give talks on it and write papers about it. So that's kind of what research looks like. In terms of the path to going to research, so the first step is majoring in math or something close to math. And taking a lot of higher level classes. So when you get to the higher level classes, you have different areas. You have abstract algebra, which is kind of like generalizations of algebra. You're not just doing algebra on numbers, but you're doing algebra on symmetries or on shapes or like any kinds of things. It's really trippy. Like imagine working with an equation, but every one of the terms isn't a number, it's actually a shape. That's actually what I do in my research. So there's also analysis, which is generalizations of calculus. This is applying calculus in lots of different settings. Doing calculus, not just on the line, not just on the plane, but in any kind of space that has differential structure. There's lots of other, there's combinatorics, there's graph theory, there's probability theory, there's geometry. So there are all these higher level classes. So you take a fair number of these to prepare for grad school, because when you do graduate work in mathematics, you want to have a fairly broad base of mathematical training. Undergraduate research is definitely a plus for graduate school, although it's actually not required. So for undergraduate research, you typically do something that's called an RU, a research experience for undergraduates, where you join as part of a team. And so with the guidance of a faculty member, you work on a project and you get a taste of research. Then when you go to graduate school, you go in, you get a master's, you get a PhD. From there, you either go on into academia or you use your incredibly highly developed math skills to do one of a number of different jobs. So that's just kind of a brief overview of that direction, that trajectory in mathematics.
Thanks. I know you explained a little bit, but if you could explain a little bit broader, just the varying, is there only one major in the math department, or are there varying tracks that you can have in terms of?
Oh yeah, so they're actually so you mean for undergraduate majors or?
Well, for undergraduate first, yeah, and then maybe we can talk about masters.
Right, so there are actually 5 undergraduate majors. There's a major in math, but there's both a BA and BS version. There's a major in actuarial science, both a BA and a BS version. People sometimes double major with these. So for instance, sometimes people double major in actuarial science and economics, or people might double major in mathematics and computer science. That's actually a very popular double major. And then there's also a BA in statistics. So we actually have 5 programs. They have similar requirements for the core courses, like you're taking calculus and linear algebra and number systems no matter what, but then in terms of what you take for higher level courses, the focus becomes different. So that's for undergraduate. For graduate, there is also, there's a 4+1 master's track as well. So you can also, there's an option to get an undergraduate degree, but in the process, you're also working towards a master's degree, and then to take a 5th year and get that master's degree.
Another question about Google, maybe this could be our last one. So they have mentioned that Google has attained quantum supremacy. So what does that really mean? And will it change the way that
I don't know.
the way of the future?
It sounds ominous.
Yeah. Yep.
More ominous than an army of monkeys.
So just to wrap up, maybe share some thoughts you have about Binghamton's math department. Maybe what drew you to the math department. What are some other programs, things that students can get involved in, or just in Binghamton in general that kind of make it stand out from other various academic departments and other schools? Yeah.
So I think there's something that we really get here. That's really important, that when we're teaching mathematics, we're not just teaching you content, but we're teaching you how to think. And that when you're a few years out from college and in the real world, that's actually going to be the most important thing that you take away from your college education, is not just the specifics of what you learned in your classes, but the process of how to attack problems that you haven't seen before, how to break them down, and how to go from the state where you don't know what to do to a state where you've completely mastered the problem and solve it. And so in a class like number systems, our intro to proofs class, when I'm teaching this class, this is really what the focus of the class is. It's about how to think. It's about challenging yourself with something that is an entirely different kind of math from what you've seen before. And learning not just how to master that mathematics, but how to reorganize your brain so that you're better at tackling the unknown. That's something that we really care about here. And that's something that I think is maybe even more important than the specific things you learn in math class. Because no matter how the economy changes, no matter what the future trends are, I can't predict what the next big thing will be after big data. What I do know is that if you know how to think and you know how to solve problems, that you will always be well prepared for what's ahead.
Thank you so much, Carrie. I think that's a great wrap up on. So I wanted to thank everyone who stayed with us till the end. I hope those answers to the questions were enlightening. I know I learned a lot as well. So we just want to thank everyone, and thank you again, Carrie, for taking your time for doing this. I think our attendees have really gotten a lot out of it. So this will also be available on our website, posted after we conclude this. So if anyone missed parts or would like to go back and watch it, share it with friends, it'll be available there. So just want to thank you again, Carrie, and we'll hope to see everybody here in the fall soon.
Thanks so much.
Bye.